Okay, so thank you, PCMI, for giving me this opportunity to present some experimental investigation with X-ray. So as you see, we are using synchrotron radiation, and we are at Soleil in a French Soleil facility. And I'm going to present results on photodisruption of ices. So we are interested in cold regions of interstellar medium where ice are formed. So we know from observation in the infrared spectroscopy towards protostar that these mantles are made of water and over carbon containing and nitrogen containing molecules, including methanol. I'm going to speak about methanol later on. And we are interested in the cycles between the solid phase and the gas phase. So, of course, we know a lot about the disruption induced by heating, but we know less about disruption that we call non-thermal disruption induced by cosmic rays, for example, or induced by UV or X-ray radiation, and especially photodisruption on which we are focusing in this study. So photodisruption, we know it's an important process that can explain, for example, the presence of gas in PDR, for example, due to VUV, but also in outer parts of protostellar envelopes, and in some extent into cores. But for X-ray, of course, it's in protoplanetary disk, as Emmanuel has shown us before, that you have strong emission from the central star, but you have also emission from the background that can reach some layers in the disk and induce the disruption. And of course, depending where you are, you can have different stratification, as Emmanuel has shown. And you can find some region where X-ray can penetrate, where UV are already attenuated. So it's really important to know to constrain the disruption yields to compare with cosmic ray-induced disruption and to know if they need to be taken into account. There is also a theoretical need because, in a sense, when you look at models, generally people calculate the energy deposited in the mantle, and then they can deduce when size at which you can evaporate your ice. So it's a heating process that it is generally modeled. And as we will see, there is an additional effect that need to be taken into account, which is a direct disruption of macroscopic samples. Okay, so what we do is that we install an ultra vacuum chamber on a sextant beamline, so a beamline optimized in the soft X-ray range. We are working around 500 eV, and this is a line well adapted due to high photon flux. Okay, so what we can do is that during irradiation, we can continuously measure different things. We can measure the positive and the negative ions that are ejected from the ice. We can measure the neutral disruption flux. So this is made by two mass spectrometers. And in the same time, the ice that we grow on a cold substrate is isolated electrically. And because during irradiation, there is a loss of electron, it induces a current that we can measure, what we call the total electron yield. And this current gives you an idea about the absorption of the ice by the photons, the photon absorption by the ice. Sorry. So we can measure this simultaneously. And let's see this example with a water sample with a 100 monolayer here that has been grown on copper. So we see in black the photodisruption signal as a fraction of photon energy. And you see in red simultaneously the total electron length giving you the absorption. So you see that they match perfectly. And what we do observe, we observe a lot of products from the ice. We do observe a large variety of cations, of ions. So the most desorbing cation is H+, with some yield. So here with a calibration that I'm not going to detail here, we are able to estimate the number of molecules per incident photon. So you see, for example, that for H+ is in the order of 10 to the -4 molecule per photons. But the surprise was to discover that not all molecules, in particular water itself, are disarming with much higher rates. And this was a surprise when we did this experiment. So if we go back to the spectrum, you can divide it into parts. So in blue, we are below the ionization of the oxygen atom. So we just excite the 1s orbital to the higher lying orbitals. And then in the red part, you see that we have an oscillation here, and then we have a constant yield. And we just, which are above ionization, so we ionize the oxygen atom. So in both cases, we have a situation where we have a core hole, and this hole in 3 femtoseconds is the atom is relaxing and inducing the desorption of a very fast Auger electron. And this is this Auger electron that is going to collide to other molecules, surrounding molecules, to produce secondary electrons and excitons that can migrate up to the surface and induce the desorption. And we believe that most of the signal I show you after are really dominated by this effect. That means it's an electron stimulated desorption that is dominating the process. So it's an indirect process. So if we take the yield that you have obtained for, above ionization, and we take into account the absorption cross-section, and if we consider that 50 monolayer are contributing to the desorption, we obtain a yield, an intrinsic efficiency of about 0.2 molecule per absorbed photon. And this is much higher than the same calculation that you can make in the UV range. So this tells us that the idea that it is an electron stimulated desorption is certainly good, because in that case, when you have one excitation, you can have multiple events, which is not the case in the UV. But going back to in astrophysics environments, we can take the yields that we have obtained. So we have obtained the yield in a very narrow energy range here. But above ionization, the process is the same. You have the same relaxation and the absorption effect, except that the absorption cross-section is decreasing. So we extrapolate just following the decrease of the absorption cross-section. And then we can multiply this yield by different spectral profiles. So here it's an example that Emmanuel has shown. So in black, it's the profile of X-ray from TW Hydrae. And then we can take into account that there is some filter due to the scattering by dust and gas, depending on the density. So we get different profile depending on different densities. And then we get the effective photodesorption yields ranging from 10 to -5 to 10 to -3, depending on the density. Meaning that these are yields that are in fact significant if we compare to what is used in the UV range, for example. This is typically yields that have some sense. So that means that this X-ray photodesorption for water, for example, this is something that needs probably to be taken into account in model of protoplanetary environments. Just an additional example on water, looking at the total electron yield here, and zooming on a small region above the resonance, we do observe a lot of chemical compounds. So thanks to Lafont et al., we are able to assign to oxygen bearing compounds, and showing you that so these peaks are stable when we irradiate. So it's a steady state chemistry, and we can estimate that it's about a few % of chemical products that are present on the ice here, showing you that there is an intense chemistry behind this process also. So now I switch to CO ices. So CO ices, so again, you see the photodisruption spectrum. You have a strong peak here characterizing the CO excitation. And again, we observe mainly CO photodisruption, but also CO2. We observe a lot of cation and anions, but at very, very low yields. So if we do the same job, we can extract some effective yields for a young star here, and we can compare to another type of excitation, which could be here representative of a background X-ray field. And you see that we are able to have very high disruption flux. If we look at the distant part, so below here, because we expect that CO will be present on the top of the ice at the lowest temperature, that means at the highest densities, we are in fact with disruption yield that are in the range of 10⁻⁴ molecule per photon. That is, it is a little below what we can find in the VUV in that case. Okay, I would like to show you some results about now organics, and especially methanol. Methanol is an important molecule, of course, because it is observed at different stage of star formation process, and it is also present in protoplanetary disk. And in that case, we start first with pure CO sample, and then we are going to mix with other molecules. So when we irradiate pure ice, we do observe a spectrum at always in the same spectral range. And we have some peaks. We observe a disruption of CO2, for example. Also, if you look at the disruption of CO2, you can recognize here the first peak, which is just exactly that I've shown before. It is the peak of CO absorption, meaning that in that case, the first peak is due to CO absorption, the second peak is due to methanol absorption, but both are creating electrons that are going to induce the disruption. But it's more indirect, and it tells you that there is a lot of chemistry on this ice. Even at the lowest fluence we can do, we already have some chemistry, but the yields are very high, 10⁻² molecule per photon for methanol. So we see for methanol, we have disruption rates, and we see lighter fragments with a lot of chemistry. Now we can play with that, and so it's just before, I want to go too fast. If we go back to the protoplanetary environment, so I give the example of dense region for young star here, we do have yields for methanol that are in the same order of that of water, telling us that, again, for methanol, in the case of pure or layer, it could be important to take into account this process. Now, if we want to be a little bit more realistic, we need to consider that methanol can be mixed with CO, for example. And so what happened when we start to mix? So here we put 13 CO around methanol. So when it's not written, it's 12 C. And we compare in green pure methanol, equal amount of CO on methanol, and a sample where methanol is diluted into CO. So we again see the desorption mainly of CO, followed by CO2, followed by methanol. But in each case, you see that when we dilute, we increase the desorption of 12 CO here by just surrounding by 13 CO2. And for methanol, it's about, it increased, but it is about the same, we have the same range. And we see also that we are forming over molecules, we are forming from 13 CO, we are reforming methanol, and we observe additional molecules that are desorbing that has small organic complex. I mean, here it's dimethyl ether, ethanol, or formic acid. So if you look on this size, you have the order of magnitude. You have a very strong desorption of CO2, followed by a strong desorption of methanol and the desorption of complex organic molecules. So it was a surprise to see that when we dilute, we have not a reduction of the desorption, but on the contrary, due to the continuous destruction, reformation of methanol, we increase its desorption. Now, if we change to another environment just by replacing CO by water, there is a completely different story. We do not observe any desorption of methanol at all. And in fact, we now observe a desorption of methoxy and CH3OH. That we don't, this one just that we know we don't observe in the previous case. So it's very interesting to compare. So what we believe that is happening here is that due to the presence of water, we are producing a lot of OH fragments, and OH fragments are going to react, destroy methanol, produce the two radicals that we are observing and that are desorbing, and then we are producing a lot of CO2. And this is the trend that we see when we increase the dilution here on the right side. We decrease the number of CO, we increase the number of CO2 that is formed. So maybe this picture is correct. And we believe that the desorption of CH3OH is in fact due to these two radicals that are normally recombining with H, but in that case, they are ejected from the surface. So they cannot produce the desorption of methanol. So we end up with this kind of scheme that Romain Bazalgette has proposed, is that finally, if we go back to our protoplanetary environment, so we are in a situation for methanol that in the surface layer, we know that the UV photons are not efficient to produce the photodesorption of methanol. This comes from previous studies we have made. And basically, if you look at this region beyond the water snow line, we expect an H2O-rich environment when we will produce the desorption of radicals with high efficiency. But now, if you go beyond the CO snow line, you are going to produce the desorption of methanol and also to over complex organic molecules. So this is a kind of study that shows we can have a differentiation depending on the composition of your ice. Okay, so that's what I wanted to show you. The message was that in most cases, in the X-ray photostimulated desorption we observe is an electron-stimulated desorption, is dominated by the effect of the Auger electron. We obtain very high quantum efficiency. That means that if we look at number of molecules ejected per absorbed photon, it's very efficient in the XUV. And now, if we look at the number in protoplanetary environment, we see that it is efficient. So it's a desorption where chemistry is playing a dominant role, clearly. And as you have seen just in the last example, the ice composition it has to be taken into account because it affects the numbers so that we can find. Okay, so with that, I have finished. I would like to thank Romain Bazalgette, Rémi Dupuis, that have worked a lot on this data, the collaborators, and a special thanks to PCMI because this is thanks to PCMI that this experiment could be developed at first. Thank you for your attention.
Thank you very much, Jean-Hugues. It's a nice talk. So there are some questions by Patrice Tellet. The first one is the X-ray induced ice chemistry different from the UV induced one?
Yeah, yes, completely. First, there is a difference in the intrinsic difference since the VUV, you are photodissociating your system, then you have a chemistry which is mainly a surface chemistry. And because it's on the surface that your fragments are going to diffuse and react and make the disruption. And here you are producing electrons that are traveling inside the ice, and on their tracks, they have a high energy. Okay, so on their tracks they are exciting a lot of excited state that are going to react. So it's I would say it's not difference in the sense that it's not automatically opening new routes, but it's a more rich chemistry. If I can answer I like this after, of course we should look at specific example to discuss more precisely.
Also another question, can you make the difference between CH3O and CH2OH?
No, we can't. Okay, so we are using mass spectrometry, so we only have the information of a ratio of a charge over mass, but we cannot know which one is it.
And so there is also a question by Emmanuel Nartois. How do yields compare? How do you compare?
Per energy deposited. Because the yields are given per photon, but an X-ray photon is 1 keV. So.
Oh yes, you mean I could make a comparison per EV deposited in the ice, okay?
Yes, because if we want to compare two sources, I mean the flux in UV and in X-ray is generally given in energy, not in number of photons, because you will have much less X-ray photons.
Okay, but it's
even if you have the same amount of total energy.
Well, so if I go back to the example of water I have given, so it's the same trend. So even if you go back to, okay, I will add in another occasion. If you express your number in terms of number of molecule per EV, you will find that X-ray dominates against the UV by more by 1 order of magnitude. The difference is not so high, but it's still significant.